Molecular electronics was a brilliant proposal. And when 25 years before, a year ago, when I started my PhD, at that point of time, molecular electronics was one of the finest proposals. And it was said with a huge campaign, as it happens in all research fields, that molecular electronics will change the world forever. What happened is it was hype, and there was a proposal even that within a single molecule, entire computer will be encoded, just like in today's proposals in quantum computing. And then a single molecule will serve the entire purpose. It will be incredibly fast, and within a single molecule, you can store all the informations. In 1 gram of water, they could say, uh, you can store all the information, all the knowledge of the humanity. So, what happened, and why molecular electronics failed, and why so many postdoctoral fellows who thought that their career would be in molecular electronics didn't get a job and silently disappeared. So it happens in the history of mankind. When science progresses, many research fields come up, and then finally several PhD students and postdocs come up. And by the time they come out, and after doing a few postdocs, they find that the field has shrinked. It does not have any or much potential. And finally, they go to other professions. And nobody actually makes a documentary on those people who trusted the scientists. So today I will dig into molecular electronics, where I was directly involved and spent a decade at least of my career in understanding molecular electronics and doing work on molecular electronics. So the first thing that created problem of molecular electronics was, if you take a molecule and put two atoms at both sides, then that atom will have will not have discrete energy levels, but a plasmonic state is there. Plasmonic state means, in metal, what happens is valence band and conduction band is there. Of course, single atom cannot have valence band, conduction band, but when you have one atom, a part of the molecular properties survive. But if you go on increasing 2 atom, 3 atom, 4 atom, Gerhard Meyer from Germany did a brilliant work to show that if more number of atoms are added after 4, 5, 6, 7 atoms, uh, the junction property dominates and the molecular property disappears. In this kind of situation, how can you scale up different molecules and their properties and create diversified properties? The same problem is with quantum computers, that one quantum computer is fine, but when you have multiple modular quantum computers and you want to integrate them, you face some serious problems which nobody talks about. The same thing happened with molecules. Nobody talked about that when you have, even if you make the junctions and try to take the information out, if it is electronic, of course, it's quantum information. But the quantum information, the devices that are taking the quantum information is an integral part of the quantum system. So this many people don't understand. And in the quantum computing, quantum computer development, the research field is facing the same problem like the single molecule electronics field, where I worked during my PhD and then later for 4 or 5 years.
Marianne Neal, Canada Geometric Language Tensor, WhatsApp audio.
So suppose you are doing a quantum measurement, a quantum state, say, function psi, you want to do the measurement, and you need to understand the wave function or Wagner function, and you want to do quantum tomography to find out how the density matrix of that wave function looks like. If you want to do that, what you need to do is to fine tune different sensors simultaneously and divide the quantum state into multiple different Adler states or copy or replica of them, and simultaneously do the measurement at the different conditions so that entire matrix is out. But if you think that all those sensors are independently measuring it, that's not true. So what happens is the quantum state psi entangles with those instruments and behave collectively, and depending on the geometry of those sensors, they emerge. So there is a fine one-to-one correspondence between the problem that we are facing in today's quantum computers and the problem that earlier people faced with the molecular electronics. However, you will find that in the people who are the architects of molecular electronics, they never concentrated on that particular part, and the architects of quantum computers also never concentrate on this particular part. That's why you will find that most of the quantum sensors that we will see today are basically classical sensors, where it is presumed that all these different kind of sensors work independently and they detect independently. This is the kind of a situation. So now, this is one major problem with molecular electronics. The second thing is that a molecule, it has electronic states, as well as its conformation also gets changed. Now, if the conformational change happens, the wave function gets totally transformed into a completely different state. Now you don't know how it will come back to the initial molecular conformation. So that means when the physical orientation, the angle, orbital, angular positions, and other things change, when the electric field is applied, the different electric field is applied or electromagnetic field is applied, the molecule undergoes a structural change, and accordingly, the change happens in the density matrix. Now, this particular feature had to be studied, and we did density functional theory. You may think that density functional theory is the most credible way to understand quantum information, because we are getting the density matrix in the most profound way possible. But if one electron gets inside a molecule, the electron is distributed in different percentage with the different atoms. So you end up in a different wave function. So what happens is that this density matrix that you are getting, that density matrix gets non-algorithmically changed. Why non-algorithmically? Because we do not understand how quantum mechanics works. What we see, it's expression that comes to the classical world. Now, we do not know the mechanism or the fundamental lying mechanism that gives birth to quantum mechanics, fundamental mechanism that give birth to superposition, entanglement, retroactive properties that often we see. For an example, one particle disappears from here and appears over here. That is called quantum tunneling. So even this particular phenomenon, its original mechanism, we don't know. We have no idea. The same problem that molecular quantum computers are facing now, we faced in molecular electronics. So the quantum state could change depending on the participant's configuration and its shape. So where through the wave function passes, how different density of matrices behave in a 3D arrangement or system. So when we didn't have any clue or idea about it, then every part makes a contribution. So you are creating a single photon source. It property changes something, and then you do some quantum circuit, and then supporting quantum circuit, then sub-supporting quantum circuits, and finally your measurement systems, the deconstruction of the wave function and other things. So you are modulating with a different way. So today in my lab, if I do it a little bit this way and you do that way, our results would differ. Certainly differ, because they will also take a part of it. And molecular electronics showed that if that is the situation, then the field is going to die. The reason is that if the molecular conformation changes, a single molecule, if conformation changes, then you need to redistribute the entire electron density of states density functions. And from that particular point, if a molecule, if conformation changes A, B, C, D, we know that one or two or three conformations. But do you know there are thousands of different conformations molecule goes and then it comes back? 1,000 is a very generous word. It could be millions of conformations. So when it happens and it comes back, then the situation is very different. So we have many different states where when it comes back to the initial one. And we find that that every single state to other state we cannot predict. Is if it is as if somebody is appearing and disappearing, disappearing and appearing, disappearing and appearing. So this network is going on in a complex relationship. So that's why molecular electronics died, because we could realize it reproducibly in laboratory. When we have a planar static molecule which does not show any conformation, but when we try to embed some functional property into it, then we needed to transform into many different conformations. And whenever conformations would change, then there will be a problem. So that means if everybody makes a similar identical quantum circuit, similar identical sensors, they will get similar results. But if there is a change in the quantum circuit, some sensors goes up and down, some sensors measures more precision, less precision, phase angular quantization or phase squeezing property changes. It is almost similar, analogous to the molecular electronics problem that people faced. So if we are not careful, then the field of quantum computer will die the same death like the molecular electronics. And unfortunately, you will never find this kind of approach or this kind of understanding or this kind of conversation. People are more busy in showing that there is entanglement, there is that's why it is a done deal for molecular electronics, or the done deal for quantum computing. So I would like to say that there are many other reasons for which molecular electronics died, and these two are the primary reasons, where scaling up or integrating and creating different conformational or functional molecules. The same problem is now faced by quantum computers.